Hi there! Welcome to the University of Sydney Mathematics Extension 1 Bridging course. My name is Colin and I'll be one of your instructors. The syllabus is comprised of 11 days worth of material, with the stuff from each day taught over a number of modules. The purpose of this introductory day is to provide a solid understanding of elementary functions along with their properties and derivatives, which is essential to every university calculus course. Let us begin by revising some key concepts of functions. Recall that intuitively, a function is a rule which takes in inputs and produces outputs. Moreover, these outputs must be unique, in the sense that only one output can result from every input. A function can be represented by a table or graph, but is most commonly given as a formula. For instance, the doubling function, given by the formula f of x equals 2x, doubles any input. For instance, the function maps 1 to 2, 2 to 4, 100 to 200, minus 5 to minus 10, etc. Terminology-wise, since x values can be chosen freely and independently, and f of x clearly depends on our choice of x, the variable x is therefore called the independent variable, and the resulting f of x is called the dependent variable. Associated with every function are the notions of its natural domain and range. The natural domain of a function is the collection, or more formally, the set, of all possible inputs. In other words, it's the set of all the possible x values for which the function makes sense. For instance, since there aren't any numbers which can't be doubled, the domain of the doubling function, f of x equals 2x, is the set of all real numbers. The range of a function is the set of all possible outputs. More precisely, it's the set of all values of f of x, as x runs through all values in the domain. We claim that the range of our doubling function is also the set of real numbers. This is because every real number is the double of some other number, so every single real number is potentially an output for the function. Since the range of a function is essentially the set of all possible y values, it's often wise to sketch its graph. Indeed, having graph sketching skills can prove quite advantageous for working out the range of more difficult functions. Alright, let's take a look at the domain and range of some basic functions. Consider the simple quadratic function f of x equals x squared. Since every single number can be squared, the domain is therefore the set of all real numbers. Here's the graph of the function, a simple parabola. From the graph, it can be seen that the function takes all positive y values, including 0. Therefore, the range is the set of all positive real numbers, including 0. Let's take a look at another example. Consider the function f of x equals 1 divided by x. For what values of x does the function make sense? Well, it makes sense to divide by any real number except for 0. Therefore, the domain is the set of all real numbers, not including 0. Here's the graph of the function, commonly known as the rectangular hyperbola. From the graph, it can be seen that the function takes all y values except 0, so the range, just like the domain, is also the set of all real numbers, not including 0. Here's another example. Consider the square root function. Since it doesn't make sense to square root negative numbers, the domain comprises the set of all positive real numbers only, including the number 0. Here's the graph of the square root function. From the graph, it can be seen that the function takes all positive y values, including 0. So the range, just like the domain, is also the set of all positive real numbers, including 0. Let's now move on to the topic of notation. In mathematics, a set or collection of objects can be written down rigorously in what's called set notation. For instance, the set of all positive numbers, including 0, can be expressed in the following way in set notation. Let's briefly examine how the notation works. First of all, the enclosing braces signifies that we're talking about a set of mathematical objects. The set between the x and the r stands for is in or is a member of. The vertical line in the middle of the expression means such that. Terminology-wise, members of a set of objects are called elements of the set. For instance, 5 is an element of the above set, while -2 is not. Despite the abstract nature of the notation, you should realize that the syntax is designed so that the expression is read from left to right like a regular English sentence. Take a look. Reading from left to right of the set above, we get the set of all real numbers x such that x is greater or equal to 0. The above set can also be written in what's called interval notation. Here, the square braces indicate that 0 is in the set, while the round braces indicate that infinity is not, since infinity is more of a concept in mathematics, as opposed to an actual real number. A word of caution, please don't get the notation confused with xy coordinates. They look similar, but are of course completely different things. There's an important difference between set notation and interval notation. Whereas set notation can be used to express any set of mathematical objects, interval notation can only be used to write down certain sets of real numbers. More specifically, interval notation is mainly useful for describing a continuous set of real numbers that are bounded by two values. These special sets are called intervals, hence the name interval notation. For instance, the interval of all real numbers greater than 1 but less than or equal to 2 can be written as the following in ordinary set notation, or in the more concise interval notation. Let us now briefly engage in a revision of the main elementary functions, starting with the exponential function y equals e to the power of x. To be successful in your mathematical studies, you'll need to be very familiar with the basic properties, including the graphs, of all the basic elementary functions. Here's another basic elementary function, the natural logarithm function. Note that the domain is the set of all positive real numbers only. Here's the sine function, which oscillates between 1 and minus 1. Here's the cosine function, which also oscillates between 1 and minus 1. Note that both sine and cosine are periodic, with period 2 pi. In other words, both graphs repeat over intervals of length 2 pi radians. In addition, you will need to be well acquainted with linear, quadratic, cubic, and perhaps higher order polynomial functions. Finally, you will also need to be familiar with the absolute value function. Alright, to finish off our first module, here's a summary of what we've learned so far.